Okay, so good morning. So before joining the meeting, I received the note from the committee asking me to give another talk. So this is the talk is just to give you some summary what I did last 20 years. So the title is the neurodegeneration study from the molecules to the big animals and finally to the human being. So I will give the four topics. So the first is the type 1 APP, Alzheimer signaling. And the second, I will talk about the fetal stem cell in adult brain. And the third part is the AD, PD, AIS, big animal model, pig animal model. So finally, I will talk about about the myelination in the human being. Yeah. So as we know, so the most of the group is interesting under the APP is the amyloid precursor protein, and the most of the group in the last 20 years is focused on the extracellular part, particularly the A beta. So our group mainly the focus on the intracellular part, the APP intracellular part, this domain. So in 2008, we, this part actually I will give in the presentation more detailed information in my second, the talk. But here I just briefly, give some overview. In 2008, my group, identified the Alzheimer's signaling. So we find that the molecular type 1 is extracellular adhesion molecule, and both type 1 APP molecules expressed under the surface of the neural stem cell. And the type 1 APP extracellular interaction can trigger the AICD, APP intracellular part release after cleavage by the gamma secretase, and the release of the AICD can bind to the Fe65, migrate into the nuclei. So after migrating into the nuclei, so this molecule may play some role in suppression neurogenesis. So after publishing this paper, we asked the question, so how the AICD, after the migrate the nuclei, what's the function of this? What's the detailed mechanism the AICD played in the nuclei? So they had two hypotheses for this. One is the AICD may directly, modulate the target gene expression. So this already approved by the several groups. For example, AICD can work as the transcription factor, modulate the expression, P53 and EGF receptors. So we asked the other question. We set up another hypothesis. We asked whether AICD can go through the, regulate the microRNA function, then indirectly modulate the target gene expression. Maybe this way can help us find the new, new way to, for the AD pathology. So we did the experiments, so with the transfected the AICD into the neuroblastoma cell, and we did the chip-seq experiment. Actually, this experiment we started did in the 2007. That time, just developed this technology in the Singapore. So we, after transfecting the AICD into the cell, we used the AICD antibody specific pull down the fragment which bind into the AICD. We did the sequence, all this sequence, to try to analyze the binding domain of the chromosome. So this is the result. We did twice, the AICD chip-seq analysis. So this is two experiments. You can see it's about 280, the the domain, the microRNA domain, modulated part is overlap, almost 70% overlapping. So this more, indicate this experiment is more, the reliable. So finally, we through the screen, we find some, about the from this 200 microRNA binding domain, we select about the top 20, the binding part. We find that it's about the, we identify the, screen about the 15 microRNA binding, promoter region. We further, confirm in the neuroblastoma cell, and also this confirmation we also did in the human neural stem cell. Finally, we found that the 4 microRNA is expressed in the human neural stem cell, which modulated by the AICD. So this is some result. We further confirm, use the neurogenesis assay, to further confirm this 4 microRNA. Finally, we find that, only 1 microRNA, MER66, which, specific modulated the expression, modulated the neurogenesis. You can see the overexpression, the microRNA MER66-3, can, deregulation the neurogenesis. And this is the, facts result. This is the, just by the counting, the result. And we can also, expressed in AICD together with the inhibitor of the MER66-3. So this co-transcription can reverse the decrease of the neurogenesis by the AICD. The further study, I will give you the more information about this story later in the second presentation. So let me give the summary. So we can see in the extracellular part, if the APP interaction with the TAG1 can trigger the cleavage with the intracellular part of the APP, the AICD release of the membrane. After the AICD release can migrate into the nuclei, and this migration can further, let the AICD work as a transcription factor, not only for the target, the directly target, for example, the P53, but also they had the targeted, the candidate is the microRNA. And for example, this MER663, which can further modulate the targeted gene and involve in the neurogenesis. I will give you later about this part. So my lab also interesting to work on to answer the question, how the younger stem cell, for example, from the embryonic, from the cord blood, from from the cord tissue and from the other younger cell, how this younger cell, interaction with the old environment after the transplantation. So in 2005, my group specific asked the question, so during the pregnant, so whether the fetal cell, we asked 3 questions. During the pregnant, whether the fetal cell can migrate to mom's brain. So if this cell can migrate to mom's brain, whether this cell can differentiate into the neuronal cell. The last question, whether this differentiate the neuronal cell plays the function to involve in the repairing the damage in the mom's brain or spinal cord. So we designed the experiments. We used the green father and the cross with the white mother. So we try to the cross after cross, we try to find the green cell in the mom's brain. So definitely, we spent about several years. We found the cross of the cell from the baby to the mom. This is the new scientist report, the baby to the mom. So we can see the baby's cell. Oh, the color is not right. This is the baby's cell. Just cross the blood, the wall of the blood vessel in the brain, they just migrate into the mom's brain. And this cell, after migrating, the mom's brain can differentiate into the neuronal cell. And also can differentiate into the oligodendrocyte, and also can differentiate into the astrocyte. And to further confirm this cell definitely from the baby, we also did the the staining with the Y chromosome antibody. So we've confirmed this cell can definitely come from the the baby. So this is the first report. The baby cell during the pregnancy, the baby's cell, the fetal cell can cross the two barriers. So one is the plasma barrier and also the BBB. Get into the mama's brain. So this is the first time you can see the Scientific American and the New Scientist all gave the the report about this work. So we still didn't answer the question whether this cell, after migrating in the mama's brain, can play the function role involved in the regeneration or repairment. So we further designed these experiments. So this is unpublished data. So we still use the grandfather. We use the mom, maybe come from the PRP transgenic mice, which is the specific demyelination of the 3 months birth. And we also tried the SOD1, it's a specific motor neuron degeneration model. So cross them, then so we check what's happened. Today I can show you some result. It's a PRP transgenic mice. You can see, you cannot, so this is, the color is not right. Okay, anyway, so you can see this is the damage of the mama's spinal cord. All this green cell actually come out from the baby. So when I first time to look at this picture, I was so moved. You can see the baby work how hard to help the mom, which have the damage in the central nervous system. So here I can give you some example. You can see this is the unmarried PRP transgenic mice. So these mice, as I mentioned, after 3 months, they started the demyelination. You can see it's, the leg is very, very weak. It's demyelinated mice. So you can see here, this is the mom after deliver 2 months. Yeah, this is the mom, after deliver the baby 2 months. So you can see the mom is that very strong leg, very strong leg. So this means the fetal stem cell, not only can migrate into the mom's, central nervous system, brain and the spinal cord, but also can, play some role for the recovery, the repairment of the damage in the mom's, the brain or the spinal cord. So this work we will continue. So next topic is about the AD, PD, and the AS, pig models. So before joining the Monash University, I worked as the director in the GSK, GlaxoSmithKline. I'm specifically in charge of the drug screen for the neurodegenerative disease, include the AD, PD, and the AIS, the MS. So we, all these big company, the last 20 years, 25 years, spend billion dollar the money, so the US dollar, so but didn't, have the great achievement for the develop the drug, for the neurodegenerative disease. So the one big problem is that when we, did the good job in the, preclinical study in the mice, then after some compound work very well in this mice model. When we move to the human being, it's almost 90% failed. So that time I suggest that maybe we can start to use the big animal model. So for the big animal model, everybody immediately think in addition to the human being, so maybe we can start to use the monkey. So the monkey definitely is a good model, but the morally still have some problem, and the cost also is quite big. So for the monkey, the one big problem, after administrate the drug, you cannot kill the monkey. You must allow the monkey naturally die. So every time when I start to, when in time to use the monkey to do the experiments, I come to ask my son, so can you help me to take care the monkey after, because some monkey can live longer than me. So my son said, this is your business. It's not my business. So that's why I think that, in addition to the monkey, what we can do? So we decide to develop the pig model. So the pig model, that time I organized to develop the pig model for the AD, for the PD, and also for the AS. So here you can see we did the transgenic APP tau. You see, like Claude just mentioned, and the PS1 transgenic the pig, and the alpha synuclein transgenic the pig, and also the SOD1 transgenic the pig. So this is the method we used, the traditional the way to develop this transgenic pig. So far we got the pig model for the AIS, for the AD and the PD, but for the AD and the PD already the pig already almost 3 years old. But we didn't find anything abnormal. But still, quite clever. The pig still not have, for example, AD pig still not have any dementia, symptom. But we successfully, get the good, the result for the AIS pig. You can see. So this is the wild type of the pig. So this is the transgenic. The SOD1 transgenic pig. This is you can see the human SOD1s, expressed in the motor neuron, and also you can see here, motor neuron. So it's very interesting, So in the mouse SOD1 transgenic mouse, you cannot find the intracellular, intranuclear inclusion. So in the human being and also in the pig model, our pig model, you can definitely see this is the clustering the inclusion in the nuclei. So you can see here. So this is the pig model. This is the white type. This is the 7 months old the pig. You can see this started the neural. Motor neuron degeneration. You can see. So our group already started the use the amnion stem cell and also some neuronal stem cell try to treat this pig model. Maybe we can use the Claude's drug, to check the pig model also, right? Yeah. So we are still waiting for the result get from the AD and the PD model. So the pig, the lifespan is about the 15 years. Yeah. So finally, let me talk about some myelination story. So in the more than 15 years ago, so we started ask the question, So why, this is the oligodendrocyte, this is the axon. So you can see the oligodendrocyte in the early stage, send the process landing to the axon. You can see the process, the oligodendrocyte specific landing to the paranode region. So they are not across the border to the node of the runway. Here is the node of the runway. So we asked the question, what's the mechanism of this landing? Why this is the process specific landing to the paranode region? So We transcribed all we know the molecular specific, which is specifically located pyranodal region into the CHO cell. We're lucky we find some oligodendrocyte which can, cell line, which can send the longer process. We co-cultured these two transfected CHO cell and the oligodendrocyte. So we try to find after the process meet the CHU cell, whether the CHU cell express specific, pyranodal molecular can stop the process, to migrate. So finally, we get we are lucky. We get the one pair of the molecular is the notch and also the F3. Notch expressed from the oligodendrocyte part, and the F3 expressed the axonal part. Which when these two molecules meet each other, they can trigger the further signaling, to promote the oligodendrocyte landing, and also the try to this signaling pathway try to induce the oligodendrocyte, a neural stem cell, or oligodendrocyte precursor cell differentiate into the matured oligodendrocyte. You can see the F3 notch signaling, and also the classical the notch signaling can coordinate to promote neural stem cell differentiate into the oligodendrocyte precursor cell. After this stage, these two pathways separate. So the F3 notch pathway can to push further this cell to for the maturation of the oligodendrocyte precursor cell, but the traditional pathway just block this pathway. So after publishing this paper in the Cell, actually we received a lot of patients, to call me. So I have the MS, so I received one father from Australia, they call me, they said, oh, my daughter every week get worse. So you publish the good paper, so can you, help us, to stop this process? So that time I'm trying to thinking how to move this research into the bench side, from the bench side move to the bedside. So we try to further try to understand whether this the pathway can promote the human bone marrow adult bone marrow stem cell differentiate into the oligodendrocyte like the cell. Actually, we did the experiment. We selected the CD90 stem cell from the bone marrow. We did the pre-differentiation in vitro. Then, so after in vitro, the pre-differentiation, we transfected the cell into the this is the in vitro pre-differentiation. We can use the F3 can increase the NG2 and O4 positive cell, the expression. And we also use the retina as the model, to injection the cell, the pre-different cell into the retina. Why we use this model? Because in the retina, they don't have the myelin. So the myelin only, form the myelin only after the optic nerve, only, out of this disc, then so form the myelin. In the inside of the retina, they don't have the myelin. So we want to use this model to see whether, the pre-differentiated human bone marrow cell can form the myelin in the in vivo. Actually, we did the injection, the pre-different cell into the retina. We can see in the retina they had the NG2 and the O4 positive cell is increased. And you can also find that the oligodendrocyte-like cell standard process, touch with the axon. You can see here is like this. And we also, to further confirm, they definitely is the myelin. So we did the EM study. We can find the oligodendrocyte, the standard process, definitely can form the one layer or two layers of myelin. So this is the first time to confirm in the in vitro pre-differentiated the oligodendrocyte in the in vivo, they can play the role to form the myelin. So the further experiments, here we can give the summary. So the F3 notch signaling pathway can promote the neuronal stem cell, oligodendrocyte precursor cell, even human bone marrow stromal cell differentiate into the oligodendrocyte, the myelin glia-like cell, which can play the role in the form of the myelin in the in vivo. So the further study we published in 2 years ago, we did the human study, to use this study we used the cord tissue and the bone marrow stem cell, the combination, treated the patient with the MS, with the MS. So we, in the early stage, we injection, almost the 5 times of the bone marrow stem cell, which isolated from the patient himself. Then, so after stabilized, we also injection the cord tissue, the stem cell, almost the 4 or 5 times, injection to this patient. So you can see the MRI, the study. This is the patient come to us 2007. You can see that they had a lot of plaque in the spinal cord and also in the brain. So this is the paper we published in the 2003. The time we did the MRI, the examination. You can see not the increase. The plaque is not an increase. The brain and also spinal cord becomes more clean. So this is the patient that we have. So the 2007, when this boy come to us, it was almost paralyzed. But after the treatment, actually, another Claude Bernard is, we visited him several times, in his family. So that now this boy can, back to the work, And the good things, the economy, he got married, so his wife got pregnant. So I told him, so let us know when before your wife will deliver the baby. So we will collect the amnion stem cell, maybe store this cell to prepare for his future, the treatment. Yeah, you can see the. And this boy right now can walk to his the hospital. Now he's the pharmacy, so. You can see now he's almost can walk. Okay, so we continue follow up this case so that we actually our group also started not only the pig animal model for the stem cell transplantation for the AIS the pig animal model. We also started to do the stem cell transplantation for the AIS patient. So under the very stringent control. Yeah. So let me summary. So I will, give the further information in my next talk about the type 1 APP, Alzheimer's signaling. So we find the fetal stem cell definitely can migrate in the mama's brain and also play some role, to involve in the repairment. So we developed the AD, PD, AIS pig model. So quite successful is the AIS pig model, but we are still waiting to get some new result from the AD and the PD animal model. So the myelination, we start from the F3 notch signaling. So we gradually spend about 20 years to gradually move toward the human being. So this is my group, yeah, and also they had a lot of collaborators. Thanks this collaboration. So let me see. Yeah, this is my group. Thanks so much. Yeah, yeah.
Zhicheng, yeah, thanks. There's an interest in using infusions of placental cell lines. That people who have money go to Switzerland to have infusions of placenta-derived cell lines, or cells extracted, grown, cleaned up, and so on. Is there any real basis for that sort of thing?
For the placental cell?
Yeah.
Yeah. So maybe the placental cell, I don't know whether they include the amnion cell. Our hypothesis, the cell to migrate the mammoth brain maybe from the amnion stem cell. This amnion stem cell, they have the very special, the role. They can avoid the immunosuppression from the mom's body. For example, the baby, definitely is something is not the mom's from the mom's body. It's the foreign stuff. Why the mom during the pregnant not the rejection of the baby. So I think that some experiments indicate that the amnion cell can deliver the signal to the mom. So, mom, hey, I'm your baby. Don't kill me. Yeah, let me stay in your body for 10 months. Yeah. So this maybe we don't know. We don't know. So we are continue to look at this part. Yeah.
Any other questions? Please, go ahead.
Who's got the ALS pigs at the moment? Are they still with GSK, or do you have?
Oh, it's not the GSK.
Sorry?
It's not belong to the GSK.
It belongs to the GSK.
Yeah, it belong to me.
Oh, I see.
You contact with me.
Okay, that'd be very interesting.
You contact with me, so we can trust your drive.
Thank you very much.